Welcome to the course Algorithmic Design. So session 8, dynamic relaxation and minimal surfaces, the type of optimization. Okay, so how are these two related? So dynamic relaxation is a numerical method for finding minimal surfaces. That's it. So numerical method meaning it is a way to compute minimal surfaces. Okay. And this dynamic relaxation also comes in sometimes in different names depending on the field. So if you're a mathematician, you can look at it from that point of view. Then it has one name, and it's a very it's a topic that is being investigated in the context of structural engineering as well. So then it has actually exactly this name, dynamic relaxation, as far as I know. Okay, but it's kind of the same thing, but maybe because it's investigated by different disciplines, it might have a bit different naming. Okay, and here I was kind of now put these definitions at the very beginning, and these are just taken from online or from the textbooks. So yeah, the aim is to, so dynamic relaxation is basically it's a form finding method. Also, we are trying to find minimal surfaces or some configuration or surface configuration. Okay, and we assume that there are certain forces that run through this surface. Okay, and these forces, because they're vector quantities, they of course they act on the nodes on the surface. Or so the surface is discretized; it has nodes. And you can think of it as, if you look at the physical material, you can think of as just atoms, or so physical particles are basically these nodes. They're just very small. But we will look at a bit more bigger discretization. Also, our nodes they have certain size and distance between each other. Okay, but the forces act through they act on these nodes, and in a minimal surface, these forces are all in equilibrium. Okay, so if you have a static structure, that means all forces inside the structure cancel each other out. So they don't, the structure is not moving, it's a static structure. And of course, in the realm of architecture, those are the structures that we are interested in. The ones that don't move, they're kind of what we build, or how we build things. Okay, so we are basically, but how to find the shape where all the forces are in equilibrium is an optimization problem. Also, we need to find how this surface looks like. Okay, and yeah, it's an example of optimization, and the parameter which is being optimized is the sum of all forces between nodes. Okay, so if you would take all the forces and see how they act on all the nodes and sum them all up, you will get one big zero, or one big zero quantity. Okay, and basically the process itself, so I'll show a little bit how it works later in detail, but we basically start with a non-optimized surface, and then we have a criteria how we change the surface in order to make it more and more move toward this equilibrium. Okay, so we are basically starting from the unknown, and we are moving towards some objective that we know, and we are changing the surface in that way. And for dynamic relaxation specifically, we always know in which direction we need to move. Okay, we know how we need to change the surface in order to make it more efficient. So it's a very straightforward process in a way, as far as optimizations go. Okay, and this is actually the algorithm, iteration steps for calculating this static equilibrium. Okay, so first, if you have a surface that has certain nodes, these nodes have position and the velocity, so they have a certain force that acts on them, which makes them move. Okay, so so first we set them all to 0. Okay, so first they're kind of not moving, so this initial kinetic energy and velocity is just 0. Then we calculate, says here, compute the geometry set. Okay, so we need to know which nodes act on which other nodes. Okay, so that's where the graphs come into the picture. If you remember last lecture, we talked about cellular automata, and we had cells, and each cell had 8 neighbors. Okay, so also here every node has neighbors, and only the neighbors act on the node. So just realized that maybe as there are no pictures here, maybe a bit hard to imagine. So, but I'll explain a little bit this even more later. So maybe I would draw a diagram and there's more pictures coming up. Okay, but basically we have to calculate this relationship between the nodes, and then basically what are the starting forces. Then it says here compute a residual force for each node. Okay, so there are forces that act on a node, and you just sum up these forces. And so in the ideal case, you will get 0, but at the beginning you will not get 0. You will get some other number or some other vector quantity. This is called a residual force. So what is left when you add all the forces? Set the residual force of constrained nodes to 0. Okay, yeah. So then there are some extra steps, like there are some nodes that don't move, and this is important. So some nodes are actually fixed, and you will see in the code later when we work, we will fix some nodes, and this is actually important. So because if we don't fix some nodes, then the equilibrium for a surface is basically to clump. The whole surface would clump into a point. Okay, that is the equilibrium configuration. So basically, if you have kind of tensile forces between the nodes, they sort of all tend to squish themselves into 0, and that is the equilibrium position. And that's of course that's just not interesting for us, because we have no use for such a surface, for such a structure that is clumped into a basically point. But if you constrain the positions of some nodes, so we say some nodes are not allowed to move, then we start getting more interesting results, more useful results. Okay, so these nodes that are constrained, we basically just say they don't move. Okay, their position doesn't change. So that's this step 4. And then as we have residual force now for each node, we on the step 5 we update the velocity and coordinates of each node. So that means we just we could, for example, just add the force, which is the velocity. We just add this quantity to the position. So we just add the vector and the position. We add them together. We get a translated point. Okay, so how does the point move in that iteration? And that's where we basically move the point. So now in the next iteration, the node has a different position. Okay, and then in step 6, we basically we go from 6 to 3. So we do a loop, and we are basically constantly calculating this residual force and updating the positions of the nodes. And this seems like now, it's not exact. I mean, it's not exactly, maybe it's evident now that this would actually lead us to equilibrium, but it is really so. So for these minimal surfaces, the way we define this problem, we will always get some equilibrium. So the structure will not, so these nodes will not move. They will not move to infinity. Okay, so they will basically at one moment the residual forces will become smaller and smaller, and we will find the equilibrium configuration. So it's very easy actually to set up these constraints so that we find this equilibrium. And yeah, and then the residual forces become smaller and smaller, and at one moment, of course, because we calculate it in a discrete way on a computer, we have to stop at one moment. So we cannot really go to 0, but we can go as small as we want. And that's it. That's kind of how this dynamic relaxation works. And basically our code that I will show you in Python does exactly this. And I could in theory just match each of these steps with each of the steps in the code. And yeah, you could kind of see exactly how they're matched. There are of course some other things in between, or there are many things in between, but it just has to do with how we implement it in Python. So there are just extra steps we have to do in order to make it work in the code. And yeah, then with dynamic relaxation, we can basically numerically calculate minimal surfaces. So it's a very kind of verbose definition. It's a surface that locally minimizes its surface area subject to some constraint. Okay, so we have so it's a surface that is basically trying to have the least area. But again, which is the surface that has the least area? It's a surface that is kind of as tiny as a point. Okay, because that surface, this area of that surface is 0. So that would be kind of the most minimal of surfaces. But again, this is not really interesting for us because this is not really a surface, it's more like a point. If we constrain some points or some areas of this surface, meaning we tell it not to move, so these are the so-called boundary conditions, then we will not get a surface that goes into 0. We will get some other configuration. And turns out that so we can get many different surfaces spanned between these constraints, but only one of them has the smallest surface, and we are basically trying to, or smallest area, we're trying to find that surface. And usually, I mean, you would kind of maybe intuitively think that, well, that should be somehow a flat surface, but you will see that from the examples, it's never flat. Okay, it's always curved, it's always doubly curved. Okay, and then basically this research became with Lagrange already in the 18th century. Basically, he was basically a mathematician, but also a physicist. So he was looking at these from a very kind of mathematical point of view. So he was first of all looking into these types of surfaces and connected them to phase spaces of physical systems and so on. So you can set the constraints in a way to get a flat surface, but yeah, but basically it's just one set of constraints. So if you set the constraints in a way, you can set the constraints in a way to get a flat surface. And I can show you in Rhino how you can do this. But basically, this is, let's say, this is just one possibility. Basically, there are a lot more configurations which give you a non-flat solution. Okay, and you will see that. So if you, for example, you see a picture here, if you put all the nodes and all the nodes and all the fixed nodes and all the movable nodes, if you put them in a plane, then this dynamic relaxation will give us this result here on the right. And this is actually flat. I mean, it's kind of the boundary is curved, but if you look at it sort of in 3D, this is completely flat. Okay, that's one solution. But as soon as you move any of these points, specifically these constraint points, if you move them, if they're not lying in a plane, this surface in between will not be flat anymore. It will be just curved. Okay, so yeah, if you somehow constrain everything to a plane, you will get a planar result. But if you have constraints that are not planar, you will get always an unplanar result. That's it. Yeah. Okay, and here it's kind of on the bottom, I have a sort of diagram that explains a little bit now how these nodes, or how we are going to think about these nodes. Okay, so these nodes can be organized however we want, but we will organize them as a grid, as a square grid. And it's only because this is just the easiest for us to do at the beginning, and it's then also a surface, or so it's like a square surface or rectangular surface. But in theory, you can organize these nodes however you want. You can organize them also spatially. And the next lecture, when we look at lattices and space frames, that's exactly what we will do. We will look at kind of more spatial configurations. But now, today, we will just look at sort of, we'll start with a flat square surface like this, and we will define these constraints, these points. We'll kind of move them a little bit in space and see sort of what results we get. Just see if I have a better, okay, so yeah, I will draw this also a little bit later, maybe better, and kind of dwell on this a little bit more. In terms of, if you look at, for example, a node in the middle, or that has four orthogonal connections to its neighbors. Okay, so there's actually not 8 neighbors, there's only 4, because you're looking here only at orthogonal connections. If you look at, for example, this node in the middle, I hope you can see my mouse. And now you can say, well, the force that acts on that node here is proportional to the lengths of these connections. Okay, so here also what we'll do, we will say the force is proportional to the distance to the other node. Okay, and this is directly related to if you, for example, have a string. I hope you can see me on a camera, because I can't actually see you. So if I have a string and I'm stretching that string, okay, so the more I stretch the string, the larger, or the string is sort of pulling back with a larger force. Okay, so there this extension or how much I'm stretching the string in terms of kind of space or length is directly proportional to the force that the string is exerted on my hands, let's say. Okay, and here we will look exactly at the same situation. So we will just say that the forces are somehow proportional to the distance. If you look at then this node in the middle, this would mean that you have 4 forces that are orthogonal to each other, and they're exactly the same if you have the square grid. Okay, so the one on the top and the one on the bottom, they cancel each other out. One on the left and the one on the right also cancel each other out. So in theory, the force that acts on this middle node is 0. Okay, so there's no force acting on it. And actually, at the beginning of the simulation, these nodes that are in the middle, they actually don't move. They don't move because the residual force at the beginning is 0. So they are kind of already in equilibrium. But the boundary, or these ones that are on the edge, they are not in equilibrium. And here I have kind of a drawing where I'm trying to draw or to kind of show this. Okay, so you have 3 forces. 2 of them cancel each other out because they're in a line. But there's a third one. Okay, third one that sort of pulls on the side, and nothing is really balancing that third force. There's nothing pulling on the bottom because we are looking, for example, at the node that is here on the bottom, or actually here. So here the edge starts to deform first. Okay, so of course these 3 forces, they can be in equilibrium, but we cannot have 2 of them aligning. Okay, so they have to all be out of alignment, and then when they kind of deform, so this node moves kind of toward the middle, it starts to form this force diagram starts forming a triangle. Okay, the triangle needs to be the force diagram. The force diagram needs to be closed. Okay, so if you were familiar with graphic statics, this is how you calculate forces in the nodes. Okay, so you look at the node, you look at all the forces that act on it, and then you assemble these or arrange these forces in a kind of a loop, and then the triangle needs to be closed. If the triangle is closed, that means this force diagram is closed. That means the node does not move. This node is in static equilibrium. And you cannot close the triangle if you have configuration that is like this, where you have kind of two lines that are they're parallel, and then the third one that is off. You cannot close this unless this third force is actually 0. Okay, so if there will be no pulling on the side, then this configuration would be in the 0. But of course, this is just a condition that this one is not pulling, and this, in this case, not true. Okay, so basically, the edge nodes will deform. They will kind of move toward inside, and then as soon as they move toward the inside, even the ones in the middle are not in equilibrium anymore, because the lengths changed, or the lengths of these forces are not the same anymore. We assume that they're in equilibrium if the forces around the node in the middle are the same, but they're not the same if the lengths start to change. If the distances between the nodes start to change, then they're as well not in equilibrium. So everything starts to move. Okay, this is in a way a flat case, but what I explained now works exactly the same in 3D. Okay, so it's just that this is the easiest way for us to think of it. Here also this configuration is, for example, when the nodes on the side are fixed. Okay, here we fix the left and the right, and then the only 2 boundaries are allowed to deform, and we get kind of something like this. I mean, this maybe reminds you of like a sock. Okay, so if I have like a stocking, stockings behave exactly the same way. So we have these woven fabric, like very elastic fibers, which are in a way under tension always. Okay, so here also we just assume that all forces are under tension. So the fabric is it behaves basically like a stocking, like a sock. And in architecture, we use them to simulate tensile structures, so for example, tents. Okay, but you can go beyond that as well. So there's, for example, this, if you were ever in London, the British Museum courtyard, the glass dome, it's like a donut kind of shaped dome for the British Museum. This was a project from Foster and Partners very long ago, I think more than 20 years ago, or already it used exactly this algorithm, okay, more or less exactly this algorithm to calculate how this, a bit small picture, but you can find in literature a bit bigger one as well. They're basically optimizing or relaxing angles between these tessellated elements, or so they're kind of more similar to each other. Okay, when we have these non-flat constraints, then the surfaces, minimal surfaces, can look a little bit like this, and they're doubly curved. So if you build them out of a stiff material, so we can create, for example, a thin concrete shells, and because they're doubly curved, they're actually very stiff. So when you look at sort of very like lightweight, thin concrete shells, they always have sort of these shapes, and often they are created either as rule surfaces or somehow relaxed surfaces between these tensile membranes. Okay, so so they have application there as well. These were some examples from last year from the students, some of the from the same code that you will have a look. So they started basically using the Python code that I will give you, and they were creating these like 10 structures, and then they just integrated also compression forces, kind of stiff struts in between them, so start to kind of stretch this fabric. So suddenly you can basically model in Rhino, and you can sort of model with these sort of forces. So it's almost like you have a stretchable fabric in a computer that you can play with. Okay, and then another application of these is that because you have something called Hooke's law. Okay, so Hooke's law tells you that if you have a catenary curve, so you have a chain that you hang. Okay, so forces in that chain, then they form this kind of paraboloid. The forces are tensile forces, and when you flip that, you get only compression forces. Okay, and this is how compression only vaults in masonry are constructed. So look at Antonio Gaudi. He used this technique directly to compute basically the vaults in Sagrada Familia in Barcelona, but this was basically used since then. I mean, these principles were used in kind of Gothic cathedrals as well, directly or indirectly. So it's not a coincidence that a Gothic, I mean, we went from Roman engineering, Roman architecture that favored arches, but like circular arches, to kind of Romanesque. So 10th, 11th century kind of Romanesque architecture in or medieval architecture basically in Europe, that also kind of just took this circular vaults as a kind of ideal, because somehow circle was considered, or sphere was considered to be ideal shape. So it should be an ideal shape for building, and that's why, for example, many Roman domes were built as circular domes. Pantheon in Rome and so on. But then we come to Gothic and Gothic engineers, and they realize that actually circle is not the best, or it's a parabola. Parabola is a better form. Okay, so, and it's because these catenary curves, and they are in when you hang them, they don't form a circular arch. They form this kind of parabola basically shape. So in order to build more efficient masonry vaults, you need to work with these sort of paraboloids. And that's why, again, the Gothic arch is like a pointed arch. So it's not exactly paraboloid, but it's sort of it's something very close to it. Okay, so you have a kind of a pointed arch is sort of as close that you could basically get there, I guess. There are some other reasons why it's kind of pointy, I guess, but basically vaults in Sagrada Familia, so built by, or still being built, but kind of initiated and designed by Antonio Gaudi 100 years ago. They used exactly these types of vaults. Okay, so that's kind of figured out. That's the shape we need. And of course, why would you use compression only in masonry? Because masonry structures are very bad in taking tensile forces. Okay, unless you have reinforcements, so you need to have some steel rebars inside, which usually you cannot really put in unless you have reinforced concrete. But if you work with masonry, you want to avoid tensile forces. And the whole kind of progression of Western, architecture from medieval times all the way to the 20th century until we invented reinforced concrete was basically figuring out how the arches need to look like in masonry. And yeah, with the code that we have, we can basically numerically compute these shapes. Okay, so we kind of skip 2,000 years of engineering, let's say, experience, and we just write the Python code, and we can get the shapes. Okay, so in a way, we could use these shapes directly to design masonry vaults. There are many examples how this is done in the last 10-15 years by people like, for example, Block Research Group in Zurich. They actually built masonry structures some years ago in Venice Biennale, 2000. Now they skipped a little bit because of Corona. I think that was supposed to be in 2020. That one was skipped, but before that, it was supposed to, I think it was 2016, where Block Research Group built so-called. I can actually maybe quickly jump to that because I really want to show you this reference. Armadillo vault. Okay, here it is. Okay, so this is Biennale. I have to check exactly which one, but this one was built. This is done with, so yeah, this is a masonry structure, so there's no reinforcement inside here. So it's just stone laid on top of a stone. And the code, this is actually done in Rhino, or kind of there's a plugin for Rhino called Rhino Vault that can calculate these types of structures. They're not really, so what we're going to do now in the code, it's a sort of a subset of what these guys can do. So you need to add a little bit more there to kind of extend how these shapes look like. But basically, these are compression only structures, and our code will also give us only, in a way, compression only surfaces. Okay, so we are already very, very close to designing structures like this. Of course, there's a lot more engineering that went into here in terms of, you know, detailing and so on. But basically, they have a plugin for Rhino called Rhino Vault that kind of started in a way that the way that we are starting here. Okay, I'll just go back. That was just one quick reference to show you. Okay, so again, minimal surfaces or these types of structures, they have application for tensile structures, so tens, but also for example, masonry structures, so masonry vaults, domes, and so on. So it's a very kind of flexible system. Okay, here I will not dwell too much, but basically, as I already talked about it, so this kind of idea that we can use graphic statics, okay, to calculate how forces flow through the structure. So if you have, for example, a spatial truss, we can actually calculate using graphic statics. We can calculate basically what are the forces in these struts. Are they compression forces? Are they tensile forces? Okay, but here, basically, what we're doing is form finding. Yes, we are trying to find a form, or in a way, a truss structure where we have only tensile forces. Okay, and yet somehow if you have a surface that basically we can project, if you have, let's say, a 2D manifold or this sort of structure surface that we can project onto a flat plane, then we can construct so-called this Cremona diagram. That's basically yeah, this force diagram is also called a Cremona diagram. Okay, so then we can actually perform certain operations in the diagram directly and go back onto the shape. And this is, because I'm not a structural engineer, I will kind of stop here, because I think I'm getting a bit ahead of myself. But basically, this type of structures are then investigated again today in computational methods, and Armadillo Vault that I just showed is just one example of where these techniques can be applied. Okay, so it is a bit more extended than just dynamic relaxation. There is a bit more happening there, but the principles of finding equilibrium of these sort of static structures is sort of very similar. By the way, this development, so the research that directly led to these, the Armadillo Vault, for example, this is only like 20 years old. Okay, so this is in a sense a cutting edge research, and there is I guess there's some researchers I know in the US that extend this to a spatial story. So you can look at so really spatial frames and look at their force diagrams, which are then polyhedra. They're not triangles anymore, but they're polyhedra in space. And you can do basically graphic statics on that as well. Okay, so that's also research that is just 10, 15 years old barely. So there's quite a lot of advancement there. Okay, and I think this is the last slide before we get to references, before we get to text here. Basically minimal surfaces. Okay, so how are these now related to minimal surfaces? Well, turns out that again we can use dynamic relaxation to numerically find minimal surfaces, even though we can also define minimal surfaces as sort of just functions. So we can, for example, just define a function that gives you the minimal surface. So there are different methods of getting these. And minimal surfaces are basically the surfaces also that appear in the physical world through soap bubbles, so soap films. So if you have these are investigations done by Aalto, okay, from Institute for Lightweight Structures in Stuttgart. I think I mentioned him already last time. So he was doing these analog experiments where he would have just a steel wire, which represents this kind of boundary, and then he would create, he would just kind of span these soap films between them. Again, soap film acts a little bit like a stocking, okay, because in a soap film, basically the soap is trying to, it just has tensile forces, okay, so it's trying to basically squeeze itself into a point. And there are reasons, or the reasons why it cannot happen is either there's a stiff boundary that keeps the edges of the film in place, or you can form a bubble, okay, so you have internal pressure. So the reason why bubble doesn't collapse into nothing is because there's air inside, okay, so the air is basically exerting internal pressure, okay, so you can actually create, in a way, soap bubbles are also a form of dynamically relaxed surfaces, but you have a bit extra ingredient, is this internal pressure that is exerted from the air that cannot escape from inside the bubble, okay. But basically, if you pop the bubble, what happens? If you have a soap film and you pop it, air comes out, and the whole film basically just kind of clumps into a basically a droplet, okay. So you never saw a soap film kind of a surface, or in a way, when it pops, it basically clumps into small droplets, okay. You can only see it if you're able to sort of stretch it. It cannot exist in a way as a surface on its own. Okay, so yeah, so there's this kind of relation between soap films, then mathematically defined minimal surfaces, and yeah, it turns out that our cells in our body and in general in nature are basically a little bit like bubbles, okay, so they have internal pressure, so there's a membrane, and then when you put them all close to each other, you get this sort of like a Voronoi formation. Somebody last time, I forgot, I apologize, the name, names escape me, but somebody asked me about the Voronoi structures, and kind of would it be an interesting, let's say, principle to look into. And then I said that they're a little bit overused, but again, if you look at, for example, soap bubbles, they form in a way Voronoi tessellations, because when you take a lot of them and put them together, their boundaries are not actually curved anymore. Okay, when you take two soap bubbles and you squish them together, the boundary between them is flat. And when you put more of them together, the boundaries between them become flat, but they become polyhedra. Okay, so you have these sort of soap bubbles that have sort of faceted or planar faces between them. Okay, and they basically form Voronoi cells. Okay, and something similar happens in certain types of rocks or minerals, but exactly because of the same principles. You would have droplets of molten lava, you have a volcano, molten lava. There are two types of rocks that melt, they mix, they cannot really dissolve in each other, but they form some kind of weird droplets. When they cool down, they form sort of these crystalline structures where you can sort of see, yeah, kind of how they interact which are okay. So these shapes, they appear in nature over and over. They're kind of almost an infinite source of inspiration. Okay, this is now we're now almost at the end of this lecture. I will just show you the readings. The readings is from Mark Burry. This one is called Scripting Cultures. So it's I think it's a whole book. Yeah. So Mark Burry is a professor in Australia. I forgot exactly where, to be honest, but he's originally New Zealander, and he's the one who is a lead architect on Sagrada Familia today. At least 5 years ago he was. I hope he still is. So Sagrada Familia is a church designed by Antonio Gaudí in Barcelona, which is being still built for the last 100 years or more. And basically, of course, Gaudí is not alive anymore, so the current head architect is Mark Burry. Okay, but Mark Burry has this very experimental approach. Okay, so he kind of just took on the principles that Gaudí was investigating. Specifically, Gaudí was using these hanging chain models to construct the walls. He just kind of took this and pushed it even further. Okay, so the idea is, if Gaudí would be alive today, he would not use analog models anymore to find these shapes, but he would probably use computers. Okay, it's just that in the, I forgot now exactly when the construction was started, but the beginning of the 20th century, of course, we didn't have computers. Okay, but Mark Burry sort of intellectually continues the work of Gaudí by basically using computers, and in his work he used then a lot of these sort of ruled surfaces, and yeah, also these catenary forms, and these are then all built in either concrete or cut in stone. Actually, I'm not sure if they're even using concrete that much, but they're for sure cut in stone. And in this book, it kind of explains a little bit this kind of merging between traditional stone cutting techniques, and some of them are inspired by techniques that are like thousands of years old. So it's not really being reinvented; they're just kind of being rediscovered, maybe, and then just using CNC milling machines, so robots basically, and kind of milling machines that are just cutting stone. Okay, but also there are traditional crafters that still work on the building. Or so you have really this kind of almost like a perfect union between the 1,000-year-old stone cutting tradition and in a way the most modern technology that we have available today. So it's a great reference to basically how the future is in a way inspired by the past. And Armadillo Vault by Block Research Group is also a great example, because somehow their inspirations are Gothic cathedrals, which are quite old, but somehow the way they examine and the way they design them now in the future is using computational means. Okay, okay, and then the other paper here, or this is a book, and this is a paper, Particle Spring Systems for Structural Form Finding, okay, by Axel Killian and John Oxendorf. I think Oxendorf is professor now at Cambridge, and Axel Killian was a long-time professor at Princeton. I think now he switched somewhere else. So they basically explain exactly the code that I'm gonna show you now. So what they use here is basically exactly the code that we will be using. So the idea is that you can create these catenary shapes and use dynamic relaxation, and you can apply sort of additional forces to them, additional external forces, specifically gravity. Okay, and then you can get these sort of hanging chain models, same as Gaudí in Sagrada Familia. And then if you invert them, you get basically compression only surfaces. Okay, so they just described this in this paper 2015. From people that are in the field, they told me that this was almost such an obvious idea back then that nobody even bothered to write a paper about it. So I think, or that's at least the impression also that I got, that this was considered to be so, yeah, kind of so obvious that, why would you write a paper about something that's very obvious? But they, I think, give this excellent context of how this can become a design tool. Okay, so look at it less from the structural engineering point of view, but really kind of as a designer. Okay, so if you're a designer, when you're designing these structures, what are the tools that you need that can facilitate this design? Okay, so that was, I think, kind of quite new, and now again we take this for granted. This is now kind of normal. So what I'll show you today in Rhino is basically exactly this. And but yeah, that's kind of just a very good reference. Okay, and the lecture is now done, but I just want to, there are 2 slides just to explain a little bit what will happen next week. Oh no, sorry, this is not next week. This is 24th, so it's the end of this month, so it's in a few weeks for the final project review. And if you have more questions about it, you are always free to ask. So this is just right up here, and I will put it even better in my courses. So the idea is that that session 11 will just be review. You'll have 5 minutes to present your project. Now this seems a bit short, but basically it's going to be 5 minutes. You talk about, let's say, very succinctly about your project, meaning kind of, to the point, and then you get 5 minutes sort of feedback. And then the idea is that you as a student need to present your project, but you also need to be a discussant. So for a project of somebody else, so you need to actually give feedback to a project of one of your peers, and I'll keep sort of track of that. Okay, so yeah, and so you have this double role. Okay, so you're presenting your project, you're getting feedback, but you also need to provide like a feedback on a project from somebody else. Okay, and then participating in this final presentation is actually mandatory for finishing the full course. So as you know, there are these 2 ways that you can finish the course. One is this, let's say, reduced version where you only get 3 credits, and there we have to, if you have need, or if you have need for that, or you want to finish the course like that, then you contact me. Some of you already did, but otherwise you need to do the final presentation and submit the assignment, and then you get kind of the full 6 credits. Okay, and in order to make this efficient, on this Tuesday, on 24th, you should send me a title of your project and a short description, 3 to 5 sentences, by this date. So it's Friday 20th. And basically, I will then compile these, and I will send them to all the students, hopefully maybe on Monday, that after. So you will basically, before the presentation starts, or before the session starts, you will have the list, the titles, and the descriptions of all the projects that will be presented. This is also important because then you express your intention to present on Tuesday, so that I can prepare to see how many people will actually submit, how many manage to finish the assignment, and so on. Okay, so so there's a bit of preparation you have to do before. Okay, and then you can also read them before the session on Tuesday, and then when people present, when your colleagues present, then you're a little bit more prepared, you know what's coming, and maybe you can then also decide, I am interested in this one and this one, and that's where I will give my feedback to, let's say. Okay, and here is a little bit how the presentation itself needs to look like. So the format is basically just a series of images, diagrams, and animations. There's no code. Okay, so you don't really need to show me code. If you want to somehow include and talk a little bit about code, you can, but this is not the focus. Okay, so I would really like to hear a little bit, encourage you to, to really think about it. Code is fascinating, and of course this was the topic of the course, that we go through code and you're sort of fascinated also how it works, and it's the hardest thing to learn. But it is also, in the end, especially when you present your projects and ideas to the outside world, it really matters actually what the code does, and that should be the focus. So in order not to get into this trap where you show me the code and then you're talking about how you implemented what, this is you really need to just focus on basically the outcomes of the code. And of course, if you have somebody who is experienced already like me, I can see immediately from your pictures how much work you kind of put into the code as well. Or I can kind of at least gauge a little bit, how would the code work, and if I have questions, I can also ask. And on the other hand, if you're showing it to somebody, if you're showing a project to somebody who is not an expert, if you show the code, you will completely lose them. Like normal people, as you maybe also know, if they are not coders themselves, but when you show them code, I mean, this is a good way to sort of stun them into basically not paying attention anymore. Then you completely lost them. They will not listen to whatever you're saying anymore after that. So yeah, the focus is not on the code. The focus is basically on the outcomes of the code. That's the idea. Okay. And then these are the questions that your presentation needs to answer very loosely. So what is the design problem, challenge, or interest your project is addressing? I mean, these rules are also great for any other design project that you do, of course, and specifically here for algorithmic design, they're even more important. So this is something universal that you can take out, I think, beyond the course. Okay, so you're trying to resolve a problem. Okay, this is a design school. We are dealing with design problems. Okay, so there's some problem or challenge, or maybe it can just be an interest that you're looking into. So what is that? Like, what are you actually trying to do? Aside from, of course, you're just learning Python and trying to write some code, but you're trying to also resolve some design problem. Okay, so that has to come at the beginning. What are you actually trying to do? Again, this has nothing to do with code necessarily. Okay, and then the second one, what is the underlying computational principle you are using to find the solution? Okay, so because this is a course about algorithmic design, you're solving your problem using computation or algorithms. And and there you should point out what are these like algorithms, or again, what is the computational principle that you're basically using? Example, you can say, well, I'm using dynamic relaxation to do form finding of catenary waltz or compression only waltz, and my design problem application is vaulting for masonry, vaulting for residential spaces or something like that in poor countries or whatever, in developing countries where they cannot build with reinforced concrete, something like that. Okay, so here you outline the design problem, but also what is the computational principle that you're using. Or you can say, well, I'm using Solar Automata to find the floor plan arrangement for I don't know, apartment building or something like that. Okay, and then okay, here I say in the third one, how do you plan to implement this computational principle using code? Here I maybe wrote a bit in the future. So how did you basically, correct way would be to say, how did you implement this computational principle? Okay, so here you maybe do talk a little bit about the code, but again, without necessarily showing the code, you can also refer to code examples from the class. So yeah, you can say, I implemented it using this and this and this. So that one is a little bit where you kind of actually refer to the code, but again, not really go into the code itself. So how is it implemented? Okay, and then on the fourth one, what else do you need for your computational design to work? So sometimes you need extra things. For example, you say, well, I'm using some images that I'm sampling, and I'm using these to do this geometry mapping. Okay, so I need these images that they come from outside, and then what are these images? So you're explaining that, or maybe some other external data. I didn't really show you in the course how to work with external data, so that's maybe some downside of the course for sure. It's just too short. But yeah, you could in theory load data from outside into Rhino. I mean, I showed you one example with just loading images, okay, and height maps or terrain. So those are the only two examples I showed, but you can kind of go even beyond. Okay, so maybe you work with real world data. So here you would kind of explain a little bit that, and that maybe, so of course, could be a very essential part of your workflow, something that you really kind of need in order to make your design work. Okay, so those are basically 4 questions that you somehow have to address, and you do it in this presentation. But your presentation, again, just images, diagrams, and if you can do animations, because they say image, what is that? Image, what is the expression? Image speaks louder than 1,000 words or something, but you could also say an animation speaks more than 1,000, 1,000 images. So often you can have a series of diagrams, or you can just show it with an animation, and then it's even more clear. Okay, so animations are a great medium to explain complex concepts. Okay. Okay, that's it.